Welcome to the second lecture video for Physics 4B. We now start with the topics that are properly in Physics 4B, starting with thermodynamics. The topics we cover this week out of OpenStax University Physics Volume 2, Chapters 1 and 2, are a bit of an odd mixture. But if you have taken introductory or general chemistry, you should find many of these topics, such as calorimetry and the ideal gas law, quite familiar. We put these topics at the beginning of our coverage of thermodynamics so that we can all, those who have taken chemistry and those who have not, start on the same page. As we start to cover topics more integral to our heat engine coverage, starting with the next lecture. So, in this lecture, we start with a discussion of thermal expansion coefficient and thermal stresses as a way to connect to the mechanical topics we covered in Physics 4A. By the way, if your Physics 4A instructor skipped Young's modulus, not to worry, these are not too important to our coverage of thermodynamics. We look at the direction of heat flow associated with different phase changes. We have some problem-solving examples involving calorimetry and, separately, the ideal gas law. You will see more examples of similar problem-solving in homework. And we cover a couple things that are more physics-oriented, in particular the kinetic theory of gas, which is how we model the ideal gas and, in fact, derive the ideal gas law from first principles. And in the last lecture segment, as we look at heat capacity of air, which will be important as we cover heat engines in the future, we also look at a slight difference between how your textbook presents thermodynamics formulas and how our lecture does them. Mainly, your textbook will use the quantity of mole based on Avogadro's number and will state the ideal gas law using the gas constant, R, which is how you see these same things presented in your chemistry classes. But because the use of Boltzmann constant, K sub B, is much more common in physics, we will stick to using the Boltzmann constant and the number of molecules directly, without introducing an extra arbitrary constant, such as the Avogadro's number. We have a lot to cover in the coming weeks. As our coverage of thermodynamics continues, I want you to set your sights on our main learning objective in our approach to thermodynamics, which is developing an understanding of heat engine cycles, operation of heat engines, and their limitations. Thermal expansion or thermal stress that's coming from thermal expansion. And I think I've explained to people who brought it up that I didn't cover it because I thought it wasn't that important, and I still believe it's not that important, and I think I might say that much in the overview video. But it's something to be aware of, especially for engineers, civil engineers. So, and really, this is the role of the textbook. The role of the textbook is to be thorough and comprehensive and cover everything, both the things that are super important and the things that are maybe not as important. Thermal expansion is one of those things that should be in the broader breadth of education of an engineer. And at the same time, if somehow we took it out entirely, we can still cover the core of our material, heat engines, without it. So I do encourage everyone to read about thermal expansion in the textbook. And, there's nice pictures. Read through it. They talk about how such potentials are asymmetrical, and there's the whole thing about how enharmonic potentials lead to the thermal expansion. Actually, upper division solid state physics classes do cover that. It's fascinating, and it'll take too much for us to get into that. I guess the part that's salient is the linear thermal expansion, which is sort of just an experimental observation that people find when temperature of a solid object or even liquid increases, they expand, and you can characterize the expansion. And the coefficient of linear expansion is that characterization of that expansion that people have measured. And this is all experimentally determined. I think there's one interesting thing I can say, which is when you look at this table of expansion coefficients, you will see that there's a relationship between the values along this column and the values along this column. Most of the cases, if you take the values along this column, multiply by 3, you'll get these values. There are some weird odd exceptions. I think I saw one for quartz. Multiply this by 3 and you do that's 1.2, which is not 1. But most other cases, take this, multiply by 3, you get that. And there's a reason for that. It's not an accident. It's not something spurious. I guess the way I like to say is there's a calculus reason for that. Let me briefly, quickly demonstrate. So that's for later. What I mean is, so imagine you have some box or a cube of material. Let's make it a cube so that it's easy for me to deal with. So you have some material of length L and depth L and height L. So it starts out at some temperature T. And it, let's say you increase its temperature. So it goes from temperature T to some temperature T plus infinitesimal temperature dt. Or it could be, it doesn't have to be infinitesimal. If you don't want to bring in calculus so early, you could start out with, some delta T, some small but not infinitesimal change of temperature delta T. That change of temperature will induce a change of length. So you will see the length change from L to L plus delta L, which will be related to delta T through the coefficient of linear expansion. And this will occur to every dimension to a degree if the expansion is isotropic, as your textbook mentions, which is most of the cases. There are circumstances where they are not, like crystals sometimes don't behave isotropically. Now, with this starting point, we can talk about with these changes, what do you expect the volume change to be? So we can start out with a description of the volume. So we started out with the volume of, it's a volume of a cube. So L cubed should be its volume. So we want to describe how much did the volume change as a result of this temperature change. So we can look at, we know what this total amount is. So we can start with that. So instead of the L cubed, it'll be L plus delta L cubed. Now, if you're just looking at this algebraically, then it's looking a little bit daunting. Although I think I can actually work this out algebraically. Let me just do that quickly. Let me write down Pascal's triangle. Is that enough? Or I think that's enough. Let me see if I can actually just write it out. So when I expand this out, it should be L cubed plus 3L squared times delta L plus 3L times delta L squared plus delta L cubed. Yeah. So, I mean, you could expand it out. And, looking at this, you might think, that looks like, it's complicated. It's not some simple expression. But this is where I say there's calculus reason, because in the limit, where delta L is infinitesimally small, because your change of temperature is infinitesimally small, there's a wonderful simplification that takes place. So that simplification is that we can ignore these terms of higher order. Ones that involve delta L squared and delta L cubed, we can ignore them, because compared to everything else, it'll be just so much smaller.
So we can say, well, that these are negligible terms. They don't matter. And um, and we retain one lowest term so that we can talk about what the effect of the infinitesimal changes in infinitesimal terms. So this infinitesimal change will lead to this infinitesimal change in volume. And now, still looking at this, I think it might look a little bit more complicated. So let me, let's see, how do I work this out? I think if I do this manipulation, it'll look a little bit simpler. It'll look more in line with the language of the thermal linear coefficient of expansion. So I'm just gonna factor out this V out of this expression. So I have original volume times 1 plus this ratio, delta V over V. You can verify that these two expressions are equal to each other. And on the right hand side, I'm going to try to do something similar. So I'm going to factor out L cubed, which is actually, that is original volume. Then what I get is 1 plus, and I do factor out two factors of L. So there's one factor of L in the denominator that I have to have. So I have delta L over L, and I still have this numerical coefficient 3. So when you are looking at this portion here, this can be expressed using the coefficient of linear expansion. And this is the factor of 3 here. It's the factor of 3 that relates this coefficient of linear expansion with this coefficient of volume expansion. So as long as there isn't some weird, odd material property stuff happening, uh, this factor of 3 relationship is what you expect to have from this kind of mathematical relationship between volume and length. So, yeah. So yeah, that's if you notice that, then great. that relationship is definitely justified. It mathematically needs to be there. And in cases where they don't, like quartz come in crystalline form, and imagine there's something anisotropic happening with the quartz. Oh, that was my 10 minutes. I wanted to talk a little bit about thermal stress, but maybe I'll just point out to some sections that you can just look at. So your textbook actually links to the previous section of the textbook from previous class, which at least in my physics 4A, we kind of skipped. So this is the last subsection in this section, thermal stress, and it goes to original lengths by methods you studied in static equilibrium and elasticity. And at least in my physics 4A, we do study static equilibrium, and we totally skip out on this stress, strain, and elastic modulus or Young's modulus. This is also one of the reasons why I didn't want to go too deeply into thermal expansion and thermal stress, because it connects to material we skipped over. But for civil engineers and people who do have to deal with the thermal expansion, this is the kind of stuff that you do have to worry about. When I was doing experimental research, I did have to worry about. My experimental research was in atomic, molecular, and optical physics, laser polarimetry. So when you have a transparent material and there's a stress applied on it that induces something called a birefringence, and that birefringence could be caused by thermal stress. So this is the kind of thing that when you're doing detailed experimental work, then frankly, you will educate yourself more than what I could reasonably teach you. So yeah, let me leave that off there. I think that's enough of topic then. um, as I said many times, that's not super important for this class, because if we took out that topic entirely, you'll define as far as coverage of heat engines goes. So. Hi, this is lecture video on phase change and heat transfer, or boiling is a cooling process. So you all know about the three phases: solid, liquid, and gas.
Or if you are sophisticated in your understanding of phases of matter, you might even know about the phase diagram, which shows different states matter can exist in depending on ambient pressure and temperature. Generally, at a given pressure, the hotter the material, the more likely it is to be in liquid phase or gas phase. Or at a given temperature, you could force gas into liquid state by applying more pressure. And this is the phase diagram for water. This is a sort of a general phase diagram for some substance that shows the same idea. The hotter the material, the more likely it is to be in liquid or gas phase. And the higher the applied pressure, the more likely it is to be in liquid phase, and possibly in the solid phase if it's in the right temperature zone. When you want to change phase of matter, boil water for example, what you normally do is transfer heat. And many of you know about different heat transfer mechanisms: conduction, convection, and radiation. So that's what forms and informs our everyday intuition. Taking water, for example, when you cool it down, put it into freezer, for example, and it freezes. It turns into solid. When you heat it up, maybe put it on a stove top, and it boils, turns into gas. There are lots of everyday experiences that go into forming this intuition. Boiling, hot; freezing, cold. What would you say if I told you your intuition is misaligned? Specifically, boiling is a cooling process. A liquid is cooled when boiling occurs. It's not an easy thing to believe, so let me show you a video. For this video, a test tube of water was placed in a bell jar, and the air inside the bell jar was vacuumed out. The water begins to boil when the ambient pressure is lowered enough so that it is equal to or less than the saturated vapor pressure of water. Intuitively, the ambient pressure was pressing water molecules together. So when the pressure is lowered enough, water molecules separate from each other, turning from liquid to gas phase. Now watch carefully. As the water continues to boil, the temperature of the remaining water starts to decrease. And if I had a better pump, I could boil this water until it begins to freeze. In fact, you can find videos where people do that by searching for the phrase freezing by boiling, for example on YouTube. But is this cooling something special that happens only with the special equipment like fancy vacuum pumps? This is where I want you to read figure 1.15 carefully. Figure 1.15. This is a plot of temperature of a substance which starts out as ice at minus 20 degrees Celsius, and you start to apply heat. On the horizontal axis, we are plotting the amount of heat added per mass. We can imagine we have 1 kilogram ice to start out with, so this would be 1 kilojoule, 2 kilojoule, and so on. As you initially add heat, the temperature of the ice increases. And this flat part is where ice is melting into water. The temperature begins to rise again after all the ice has melted, and then flattening out where water is being vaporized, that is, boiling into steam. And when all the water has been turned into steam, the temperature of the steam rises again. I hope this graph doesn't seem unfamiliar. If you have not seen this graph before, I hope this at least makes intuitive sense. After all, this is how we define a melting point and a boiling point. When you have a mixture of ice and water, if they are all well mixed into a thermal equilibrium, you know it is at 0 degrees Celsius. When you have boiling water, mixture of water and steam, as long as it is boiling at 1 atmosphere of pressure, you know it is at 100 degrees Celsius. You don't have to know how long the pot of water has been boiling to know what its temperature is, as long as there is some water left. Now, here's what I want you to consider. If, as you go along the horizontal axis, you're adding heat, why isn't that added heat showing up as temperature of the ice water rising, or temperature of water and steam rising? Your textbook talks about latent heat of fusion for melting, and latent heat of vaporization for boiling. This is the amount of heat needed to break bonds between molecules, turning solid into liquid and liquid into gas. And here is another way to look at this. This breaking of bonds takes energy. You have to put in enough energy to free a molecule that's bound to a neighboring molecule. When this energy is taken from the surrounding is cooled by this process. This is why you see, as the ice melts, the temperature of the mixture stays constant, because the cooling effect of ice melting is exactly taking away the heat input from outside. And this is also why, as the water boils, the temperature of the mixture stays constant, because the cooling effect of water boiling is exactly taking away the heat input from outside. This latent heat of vaporization is quite substantial. As you see in this graph, it takes more energy to boil 1 kilogram of water already at 100 degrees Celsius than the amount of energy it takes to bring 1 kilogram of very cold ice to 100 degrees Celsius. You can look at the distance along the horizontal axis to see how much heat it takes to boil away all the water. Over the next few weeks, we are going to be referring to internal energy quite a bit. Please remember that the kind of internal energy we will be interested in comes in two primary forms: kinetic energy and potential energy. In both cases, we are talking of kinetic energy and potential energy of microscopic objects, molecules. All molecules either bounce around in gas and liquid forms or vibrate in solid form especially. The kinetic energy, the average kinetic energy of this movement is reflected in the temperature measurements. The potential energy of molecules, since most molecules attract each other through intermolecular forces, the farther away molecules are from each other, there is more potential energy. And this is reflected in the state of matter. The solid state has the most negative potential energy. It requires the greatest amount of energy to free the molecules from its neighbors. And the gas state has the least negative potential energy. To a good approximation, it's zero for many gases at room temperature. In fact, that's the ideal gas approximation. So this internal energy isn't really a new form of energy. It is still a form of mechanical energy, potential plus kinetic energy, when you take the molecular view of matter. To wrap up this video, please think about situations when you are near a substance, well, most likely water, that was turning into gas, evaporation, or turning into liquid from gas, condensation. In which of the two did you become cooler than you otherwise would have been? In which case did you become warmer?
So this is a calorimetry question. It's one of those questions you might have seen in a chemistry class, and that's really my biggest excuse for not spending more time in calorimetry. But I do recognize the calorimetry questions. It does involve multi-step problem solving, and they can be challenging. The other excuse for my not spending a lot of time covering calorimetry questions is that we don't actually use calorimetry all that much in thermodynamics as we cover it in physics. So while it's something that should be in your background of thermal physics knowledge, as we move on to the remainder of the 3-week coverage of thermodynamics, you're not really going to see us use calorimetry. So it's the other reason we don't spend a lot of time. But since this is possibly one of the homework questions, let me just cover it, working through this one additional example of calorimetry questions. So it says some mass. Let me just start by labeling these things. Some mass, sample of water, some temperature is in a calorimeter. You drop a piece of steel. Okay, that's probably important that I'm dealing with the water and steel with a mass M2 at some other temperature T2 into it. Okay, after the sizzling subsides, what is the final equilibrium temperature? Make a reasonable evaporation. Okay. Okay. And it asks the final equilibrium temperature of water and steel. And yeah, so this is the what I keep calling calorimetric question. So the setup is that you have some body of water at some temperature T1, and you are dropping in some other object at a different temperature T2 into the thing. And I think most people have good intuition for what happens when you do that. Over time, these two things will come to a thermal equilibrium. They will, the temperature of water will rise, temperature of the block will go down, and all together they will reach some kind of final temperature. And so hopefully you have that intuition. And the way to quantify how that comes to be is we describe that with a heat. And remember, in chemistry and physics, we define heat as not the way we might talk about heat as a thermal energy heat. When we say the word heat, the technical definition is the flow of thermal energy from a higher temperature to lower temperature. When we talk about heat, quote unquote, in this class, the technical definition of heat refers to flow of energy. It's a flow of energy due to difference in temperature. So as you visualize this process, what we want to describe is the heat flowing out of this object and heat flowing into water. And in a well-insulated calorimeter, I hope you have this intuitive feel that total energy is conserved. So whatever heat out is of this hotter object, it has to be equal to the heat input of the colder object. And that's the starting place for setting the equations that you are going to solve for in a calorimetry problem. So let me write it out. We have heat out of the steel. That's going to be equal to heat into water. And this is the part of the physics problem solving that I hope you learned in physics 4A, and to the degree that you might need to review calorimetry problems where you can grease those wheels again and start to get back into practice of solving these word questions. And so you do have to know some thing about how we express the heat in context like this. this will have to come from your chapter reading, which is that amount of heat transferred can be related to something that we call specific heat capacity, that I'm going to indicate with the letter C. And specific heat capacity is related to heat transfer by that constant times amount of mass, and this together is sometimes called the heat capacity, not specific heat capacity, but heat capacity together. And what heat capacity relates to is how the heat transfer is related to change of temperature. So this is an expression that you would have to either be able to guess intuitively, which might be asking a lot, but the textbook covers it, so you can also see it in textbook. So this is something that you have to know, and once you know that and remember that, then you can express these expressions for heat input into steel, heat output out of steel, and heat input into water. In terms of these coefficients that you can look up, parameters that you've been given, and some expressions that you can relate to, your knowns and unknowns. So let me do that. I'm going to write out. So there should be some specific heat capacity of steel that I can look up later, times mass of steel. I've been given that, M2, times, and I need to write out the change of temperature. And here I'm going to do something that's a little bit unusual, and something that you do have to be careful about. So normally, most of the times when we say things like delta T, most of the time what we mean is T final minus T initial. That's kind of the definition of change in temperature. With this particular case, I'm going to make a bit of an exception, which is designed to make it so that every quantity that I'm going to write down is going to be positive. So if I just blindly do this, then here it can actually be a negative thing. But the way I wrote my equations here, it only makes sense if this is a positive quantity and this is positive quantity. So I'm going to write my equations with that awareness. So with that awareness, what I have to do is I have to put the temperatures in correct order. So I have to say, okay, the steel is going to cool down, so my final temperature will be lower than T2. So this is differential temperature here. I want to compute it as T2, the initial temperature of steel, minus whatever the final temperature is. That's going to be lower, so this whole quantity will be positive, as it should be the way I'm writing my equations here. This is an artifact of how I'm writing this equation. Okay, on the right hand side, so I should have specific capacity of water. This is another parameter you can look up, times mass of the water that's been given, M1, times the change of temperature of water. And here, after thinking through it, I recognize, okay, water's gonna heat up, so my final temperature will be higher, T final, minus the initial temperature of T1 water. So this is the more proper way we would normally write delta T. And here I swap the order of these two because of the way I studied my equation. I always want to be aware of the interaction between how I choose to write my equations and how that might affect the sign of some of the quantities. So that's my expression, and I think that might be it. So whenever I do, I go through problem solving steps like this. What I like to do before I do any significant amount of math is making sure that I have all the necessary information. And the way you do that in a general term is first you count your unknowns. You count how many things you don't know that's involved in your equations. And looking at it here, this is something I can look up, so I don't care. It's fine. This has been given, so I know. This has been given, so I know. So, T final, I don't know this. So this is an unknown, one unknown. Specific capacity of water, I can look it up. So I'm treating it as known. M1 I know, T1 I know, and this T final, it's another but it's the same unknown as this. So I don't count it as a separate unknown. So in this equation, I have one unknown, and what I'm calling information is basically equation. So that's how information is always presented in this problem solving context. Information comes in the form of an equation. Equation gives you some constraint that that becomes your information. So I have a one equation, one unknown. So and I hope this is covered some place in algebra. I forget exactly where, but somewhere in algebra you learned if you have in given a system of equations, if your number of equations are the same as your number of unknowns, and you have an independent system of equations, then you can solve for it. So I can solve for it. So let me do that. I'll just go through this relatively quickly. So what I'm going to do is I'm going to first try to collect like terms. So I'm going to try to put together all the terms with the t final on the left hand side. So that means I have these multiplied together. So minus c still times m2 times t final. And I have this t final term here that I'm going to move over to left. And when I do that, I get a minus sign. So minus c m1 t final, c water times m1 times t final. And I'm going to say, so that's all the terms, like terms I'm collecting on the left-hand side. Let me say that's equal to all the other terms that I'm going to collect on the right-hand side. By the way, I'm skipping quite a few algebra steps here, doing some of them in my head. I do strongly recommend that you get practice with algebra, that you feel comfortable with some of these mental algebra. The most important math skill in this class is really algebra. That's why I do really want to encourage people to practice. Okay, so I have the product of C m to T2. I'm going to move it over to right, so it'll get a minus sign. C still m2 T2. And already on the right hand side, I have a C m1 minus T1. So minus C water m1 times T1. So, I have a bunch of extra. So I can imagine multiplying through the entire thing by -1. And when I do that, I get to cancel out all these minus signs. When I distribute it, it cancels these out. So I have basically this sum is equal to that. Everything on the right-hand side is a known quantity. So what I should do is I should factor out the left-hand side. So factoring left-hand side, I get, factoring out t final, the one unknown I'm trying to solve for, t final times c still times m2 plus c water times m1 is equal to c still times m2 times t2. It's a number you can calculate, plus, let me just scroll a little bit, c water times m1 times t1. And if I divide through by this combination of numbers, so let me just say the same thing. On the right hand side, I get this numerator divided by c still times m2 plus c water times m1, and this cancels out to 1. So plug in the numbers here for this. That'll get you T final. And when you get the T final, you should confirm to verify that T final is in between 10.5 degrees C or whatever number generated for you, and 209 degrees C or whatever number generated for you. I'm gonna guess here it's probably gonna be around 30 degrees C maybe. Just guessing, or actually even less. There's more water than still, so 20, 30 degrees C maybe. When and if you plug in numbers, you will see. So Yeah, so that's the calorimetry problem solving. For part A, part B makes this a little bit more complicated, and I think I know the answer. So the final temperature will be um, lower, but not significantly so. And it has to do with if you have, so it's a matter of how, so you set up this equation as you're solving. Heat out of the steel goes into the water. And if you account for the glass beaker, which is in the starts at the same temperature as water, then what you have to figure out is, so additional heat has to flow into the glass beaker. So there's a plus Q in beaker, which would add this additional term here, plus C glass times mass of glass times T final minus T1. And when you go through um, the process here, you'll figure, T final is going to be smaller. But when you, I guess it's a kind of a number sense thing. When you look at the how large the specific capacity of water times the mass of water is, and compare it to the specific capacity of glass, which is a lot smaller than this, times the mass of glass, which is also smaller than amount of water, that this additional term doesn't contribute a lot. Contributes a little bit, but so that's what I mean, lower, but not significantly so. And doing part C takes more algebra. So I did the first step modification here. You have to do the remainder of the modifications starting from here, or maybe just redo the algebra, solving for T final and solving for it and plugging numbers. So, so yeah, that's the calorimetry problem. And I guess the third reason I do like doing calorimetry problems, they tend to be very tedious. So, I mean, it does involve a lot of algebra steps. So it does take a lot of time. And you will see me right now not plugging in any numbers, because if I choose to plug in numbers, that's another 5 minutes. And this is already 30 minutes over. So I would like to end this here. Hi, this is the first part of two-part videos on kinetic theory of gas, or molecular model of gas. In this first video, we will explore the conceptual ground and we will dig into the math in the second video. When we say kinetic theory or molecular model, we are getting into what we imagine gases to be made up of. Without rehashing all the ancient ideas about the 5 elements and whatnot, our current model is that of gas as bouncing balls, like this PhET simulation shows. This is state of matter simulation from phet.colorado.edu. I encourage you to find it on your own and play with it, but I will highlight some features of this molecular model. One feature you can immediately notice after playing around with it for a bit, raising the temperature and lowering the temperature, is how temperature is related to the speed of the molecules. Here's the neon gas at, wait for a bit, at 500 Kelvin. See how fast the atoms bounce around. And here is the neon gas at 125 Kelvin. See how much slower the atoms bounce around. You will see when we complete the mathematical derivation of ideal gas law in the second video that the average speed of gas molecules is proportional to the square root of the temperature. The second thing you can see, and it's easier to see with the simulation under phase changes, is where pressure comes from. Let me heat up this neon solid until it turns into gas at some reasonable temperature. (100 Kelvin), this is reasonable temperature. With this small number of gas particles, the pressure fluctuates. Using this finger, I can press down on the piston,
or just hold it in place. The force needed to hold this piston in place is related to the pressure being measured. But now, why is this force necessary? What would mechanically cause the lid to fly off if something wasn't holding it down? That would be all these particles bouncing from the lid. Each particle bouncing from the lid delivers some impulse, change of momentum to the lid, which can be translated to the force on the lid from the particles once you know the rate of collision. This is the origin of pressure in a sample of gas. The collisions of gas particles with the container, which leads to the pressure. You will see all the mathematical details in the second video, so we will hold off on the mathematical expressions until then. For now, while we have this simulation up, I want to point out one thing you will see soon enough in chapter 3. When I press the lid down, why does the temperature go up? To many people, this just makes intuitive sense. You squeeze something hard and it heats up. It's when you ask the questions of why that you realize something is missing. When you look at the ideal gas law, it contains three dynamical quantities: pressure, volume, and temperature. When you are decreasing the volume by squeezing this cylinder, that factor alone doesn't tell you anything about pressure or temperature. If you could assume that the temperature was constant, then you can figure out that pressure also goes up. But nothing in the ideal gas law says that the temperature should go up, and that as a consequence the pressure would go up even more than it would have if a temperature stayed constant. There is an energy consideration here that we'll cover more properly in chapter 3. So I will see you for the next video when we finally get to do all the math. Bye. Hi. In this video, Kinetic Theory of Gas, Part 2, we are going to dig into mathematical details of this molecular model of ideal gas. Specifically, we are going to derive the ideal gas law. So to set up our derivation, I'd like to consider a cubic volume like this. Let's say that a side of this cubic volume has length L. So imagine looking at this cubic volume straight along the z-axis from the positive z-axis. These are the walls of the cubic volume. Let's consider a single gas particle with some velocity v. You can express the velocity vector with x and y and z component. And it's going to follow some trajectory, bouncing around in this box. Now, as this gas particle bounces around, each time it bounces on a wall, it's going to exert a force. So let's try to describe that force. Specifically, this is what I want to describe. I want to describe magnitude of force perpendicular to surface. Since the motion in x, y, and z directions are independent, I think I can make this description a little bit simpler by pairing up these surfaces and describing them separately. Watch. So I will treat the pair of surfaces 1 and 2 together, and the forces perpendicular to these two surfaces outward. So to describe the force, I use the basic definition of force. I hope you remember from Physics 4a that force is not defined as mass times acceleration, but force is actually defined as rate of change of momentum. So what I want to count is the total amount of outward momentum delivered on the wall by the gas divided by how much time it took. So if I'm imagining how this gas particle is bouncing back and forth, to describe that, total amount of momentum delivered, I think I can do it this way. If I know how much momentum was delivered per each collision and multiply it by number of collisions divided by amount of time for that number of collisions. The amount of momentum change per collision is going to be twice mass times the x component of velocity. This is why. Imagine a particle moving towards the left with some x component of velocity minus vx. So it has momentum of minus mvx going in, and after bouncing from the wall, it comes out with plus vx velocity, or the momentum of plus mvx. So the change in the momentum is the final momentum plus mvx minus the initial momentum minus mvx. Do that, you get 2 mvx for the change of momentum per collision. Now, for the number of collisions per time, I think it's easier to figure out the amount of time between collisions. Then it will be one collision per some amount of time we figure out. So when you take the reciprocal of the amount of time between collisions, that's going to give you this fraction of number of collisions per time. So when you imagine a gas particle starting from left side, moving to the right with the speed of vx, the amount of time it takes to the next collision when it reaches wall number 2, it's going to be the distance, L, divided by the speed, Vx. So take the reciprocal of that, that's Vx over L. Okay, let's write that down. And the change of momentum per collision, or we can simplify this a little bit. The next two pair of surfaces we are going to handle are the pair of surfaces perpendicular to the y-axis, surfaces 3 and 4. And all the arguments will go the same way. The only difference is where we had x component, we are going to have y component. So outward force perpendicular to the surfaces 3 and 4 are going to be, imagine going through all the arguments we did before. So where we had x, replace that with y. And the expression for force here will be 2m over L Vy squared. Same distance L since it's a cubic volume. And we are going to consider surfaces 5 and 6, the two surfaces perpendicular to the z-axis. And the force for this pair of surfaces will be 2m over L Vg squared. So to calculate the pressure on these surfaces, we are going to want the total force divided by the total area. For the total force, we simply add up the terms we derived for x, y, and z-axis associated surfaces, and factor out 2m over L. And the total area is going to be area of one of square surfaces, L squared, times 6, since there are 6 faces. Now, we see some pretty cool simplifications. This Vx squared plus Vy squared plus Vg squared, I hope you recognize this as the magnitude of the velocity vector. So I can simply write this as V squared. And let me point out, I'm going to be combining this L. So I'm going to get L cubed. But then since we are dealing with the cube, L cubed is the volume, or capital V. Let me write all this down, making sure you're not confusing the lowercase v for speed with uppercase v for volume. So this is for a single gas particle Now, in usual sample of gas, there's more than a single gas particle. There's usually a large number of gas particles. So if we have an n number of gas particles, the pressure will simply scale. The forces so there will be n times the amount of force. So the pressure will be n times what we currently have on the right hand side. So for a sample of gas containing n particles, pressure is n times 1/3 mv squared over volume. Now, for no particular reason, let me collect the pressure and volume on one side, erasing all of this, and writing the expression here. So this is the expression we derive from basic physical principles that relate pressure and volume of a sample of gas to each other and to other quantities, the number of gas particles, and a bit of a thorny area here, the speed of gas particle, which is not that easy to measure. So at this point, let me compare this to the ideal gas law you learned in chemistry, except I'm gonna write it in the physicist way. Pressure times volume is equal to, in chemistry you learned lowercase n times gas constant R. In physics, it would be the number of gas molecules, capital N, times what we call Boltzmann constant, K, sometimes with subscript V, sometimes without, times the temperature. So this is the experimentally determined ideal gas law that relates the macroscopic dynamical quantities, pressure, volume, and temperature. Now, comparing these quantities, we notice something, that if both of these are correct, then these terms that I'm putting in a box must be equal to each other. Put it in other words, 1/3 mv squared is equal to Boltzmann constant times the temperature. Let me do a little bit of rewriting so that the left-hand side is more recognizable. I just multiplied through the previous equation by 3/2. The left-hand side is what you would recognize as the kinetic energy, or more specifically the average kinetic energy. There's a little bit of details of derivation that I skipped over that I'm dealing the average velocity. You can read about it in the book. So what this relationship is telling you is that average kinetic energy of a gas particle is given by 3/2 Boltzmann's constant times the temperature. So the temperature is directly related to the average kinetic energy of gas particles. So this is the derivation of the ideal gas law. Following the basic mechanical principles, we derived this expression here, where the left-hand side was equal to the ideal gas law, and right-hand side had the right terms, but had some microscopic quantities that we couldn't directly measure. But on comparing it to the experimental ideal gas law, we extracted some information that we didn't know going in, that we have a way to get at this microscopic quantity, or more specifically, the microscopic kinetic energy of gas particles. And it is directly related to the macroscopic quantity, temperature. So this is pretty cool. Let me show you just one more thing. Let's go back to the picture of a single gas particle in a cubic volume. This gas is at some temperature, and that also means it's moving at some velocity v. And as we just talked about, there's a relationship between the temperature and this velocity by this relationship. The kinetic energy, 1/2 mv squared, is equal to 3/2 Boltzmann constant times the temperature. Now, from the experimental ideal gas law, PV is equal to NKT, you know that when you double the temperature while keeping the volume the same, if you do that, that leads to doubling of the pressure. That was almost intuitive. That's how chemists just guessed at it, and that was right. Now, how would this be consistent with the picture that we developed based on the first principles of mechanics? Now here, if you double the temperature, then temperature scales as v squared. So your speed wouldn't quite double. Instead, you lead to this result. Your speed increases by a factor of square root of 2. But I somehow have to get to doubling of pressure. Well, let's go back to the definition of force. Force is rate of change of momentum. So what we talked about here, that does mean my change of momentum only increases by a factor of square root of 2. Because momentum is mass times velocity, so if your velocity increases by a factor, then so does your momentum. But here's what I was almost about to leave out. Because the speed is increasing, it takes less time for the gas particles to bounce back and forth between the surfaces. So this delta T has to change as well. So it takes less time, so it's going to be reciprocal. 1 over square root of 2 of the original delta T. So all is well. If you combine this into an expression for force, from the original value, after these changes are applied, it goes to square root of 2 divided by 1 over square root of 2, so 2 times the force. So the force on the walls are now doubled, so the pressure will be doubled. So it all checks out. So this was the derivation of ideal gas law. And although I wouldn't ask you to do derivation like this on your exams or even homework, the understanding of something like this is good to have in your head as a mental background, to know that what seems like new laws of thermodynamics that you are learning, they can be derived from the mechanical principles that you have learned all in Physics 4A. That's all, and I'll see you in the next video. Bye. Hi, this is the first video in application of ideal gas law. Ideal gas law, PV is equal to NKT, is very important to thermodynamics. It's important in the sense that multiplication is important to calculus. So thermodynamics isn't entirely about ideal gas law, but we presume that you know how to apply ideal gas law when you are going into thermodynamics. So we'll present information in such a way that you must use ideal gas law to fill in the blanks and figure out any details that's not directly provided to you. That's what I mean. It's important in the sense that multiplication is important in calculus. Calculus classes are not really about multiplication, but we assume you know how to do multiplication to be able to do calculus. Alright, so this is the simpler of the two examples that I will work out. So this is a more direct, straightforward example of ideal gas law. So you are given some sample of gas in the form of sealed bag. So what that tells you is that the number of gas particles, n, will be constant in this problem. So now the problem gives you a set of informations. It gives you pressure at the bottom where it's packed. Let me assign a letter to it, PB. and the temperature of 19 degrees C. Let me assign that another letter, temperature at the bottom. And it says when opened at a summer picnic place in some place at a temperature 31 degrees C. Let me give that another letter. This is the temperature, let's say at the top. The volume of the air in the bag is 1.39 times its original volume. This is a bit odd way of giving you the information, so let me kind of write it down. What it's telling you is that the volume of the air in the bag at the top, so V top is equal to some multiplicative factor F times volume at the bottom. Now it's asking what is the pressure of the air at the top, so pressure at the top. So it's a pretty straightforward question. You have one unknown that you're trying to solve for, and this ideal gas law is going to be your main tool. So this would be my approach. Ideal gas law involves 4 quantities that could potentially change: pressure, volume, number of particles, and temperature. In most problems, the number of particles is going to be the same. So a strategy to use ideal gas law would be to use it like a conservation law, because you can rewrite this into this form. You can rewrite it as pressure times volume divided by temperature is equal to NKB. K, Boltzmann constant, is constant, it doesn't change. N could potentially change, but in many questions it doesn't. So in the questions where n doesn't change, the right hand side is constant, meaning the combination of quantities on the left hand side under one situation at the bottom near sea level has to be the same as at the top where you're doing the summer picnic. So that's what I mean. You would use this like a conservation law, even though it's not technically. So I hope you remember how to apply conservation law from Physics 4a. Let me give you a quick refresher. So I would write down pressure at the bottom times volume at the bottom divided by temperature at the bottom is equal to pressure at the top times volume at the top divided by temperature at the top. Remember, you are being asked for pressure at the top. So I better solve for it. Let's solve for it. Solving for PT, I get PT is equal to, let me just do it in my head. All right, there it is. Well, I'm not that fast. I edited the video. So in this expression, now I think you have all the information to plug in. So you're not given the volumes directly, but you can solve for the ratio of volumes from here. So let me solve this as VB over VT. VB over VT is equal to 1 over F, seems right to me. That means what I have here is going to become 1 over F when I plug in the numbers. So in my case, 1 over 1.39. You do have to be careful with the temperatures here. In ideal gas law, we are assuming that the temperature is in absolute scale, that is the Kelvin scale. So you should convert the temperatures 19 degrees C, if that's the number you have, to Kelvin scale by adding 273 or 273.15. So you kind of want to be sure that the number that you're plugging for temperature at the bottom is 292.15 Kelvin, and the temperature at the top that you're plugging in is equal to 304.15 Kelvin. Well, so I guess temperature actually didn't change a lot.
But the tolerance for this problem is 1%, so you do want to plug that in. And you are given the pressure at the bottom, 1 atmosphere. So after you work out all these multiplicative factors, you should get the pressure at the top in atmosphere. So that's it. Pretty simple. It's the main tool you use to figure out any unknown pressure, volume, or temperature. In this question, it was an unknown pressure that you had to figure out. I'll see you for the second example, and bye. Hi, this is the second video in the examples of application of ideal gas law. So the second example is a harder question. It's the kind of question that we physicists like to ask, because a question like this forces you to remember many different relationships in physics and use all of them in trying to answer the question that is asked: how deep is the lake? And when you read this question, you might feel like, what does any of the given information have anything to do with that? This is where you kind of have to remember back to what you learned way back in Physics 4A. Something about pressure due to weight of fluid, and there was this formula. That pressure is equal to density of fluid times gravitational acceleration times the height. Oh, this is why height is coming in. So that had to be in the back of your mind, and you had to remember that. And even after having remembered that, there are some pitfalls that you need to avoid. So that's why I want you to do this as an example to illustrate what types of questions you could be asked to remember to use the ideal gas law. So here you are given that you are dealing with an air bubble. So I hope that immediately flashes something in your head that, well, that must mean the number of gas particles is constant. And you are still using the same ideal gas law. PV is equal to NKT. And maybe because N is constant, you're already thinking ahead to putting this into this format. PV over T is equal to NK, a constant quantity, kind of a conserved quantity for this question. Maybe that will be useful. We'll see. All right, let's diagram some of the information that are given. So it's going from bottom to top. It says volume increases by 85%. So we are given some kind of number for percent. If we say volume at the bottom is V sub B, then the volume at the top is greater. And we would say it's greater by a factor, not 85%, but let me write it this way: 1 plus the fractional quantities that you are given. So here it'd be 1 plus 0.85, so 1.85. All right, let's keep going. You are given the temperature bottom of the lake. So temperature bottom, and you are given temperature at the top. And you are asked how deep is the lake. So there are some informations that are not given to you. One is the pressure at the top. So this is the kind of thing you might figure out after having missed this question a couple times. I'll just shortcut to the end. What you need to figure out is that pressure at the top is going to be 1 atmosphere. It's exposed to the atmosphere, so 1 atmosphere is what you should figure out. So pressure at the top is equal to 1 atmosphere. So the pressure at the bottom isn't given, but you have this for the change of pressure. So the pressure at the bottom will be equal to pressure at the top plus this change of pressure. All right, I think I have everything. Let's start by writing down that conservation law equation. So pressure at the bottom times volume at the bottom over
temperature at the bottom is equal to pressure at the top times volume at the top divided by temperature at the top. Alright, so the temperature is given, so I won't really worry about that. The volume isn't given, but I can put the volume in ratios, and I think I know how to handle that. So what I need to worry about is I'm not given pressure at the bottom of the lake, and it's not really the quantity I'm looking for. The quantity I am looking for is the height or the depth of the lake. So I think I better plug this into the equation and plug in what delta P is into the equation. And I think that'll give me something where I can solve it for H. So let me do that plugging in things. Alright, let's make sure I didn't make any mistake in writing this down, copying most things over, and just plugging in what PB is in terms of H. And now I'm going to solve for H. It's a fairly standard algebraic manipulation. I need to move TB over to the other side, VB over to the other side, subtract PT, and then divide out by rho g. So I'll just do that in my head, write it down. You can pause the video and make sure you're following. So let's go. Alright, I think that's it. Give you a little chance to look at it, pause the video if you need to, and verify that this is also what you get when you solve the previous equation for H. Alright, once you've verified it, then all the numbers are there to plug in. So you are given the temperatures, just to make sure you convert it to Kelvin. So you will see that this ratio is very close to 1. But different enough that you can just let that be equal to 1. The volumes, you can get the ratio of the volumes from this expression here. Hopefully you have these two constants in your background knowledge, that the density of water is 1000 kilogram per cubic meter. Remember, cubic meter is rather large volume. It's 1000 liters. And G, I don't think anyone ever forgets that, 9.8 meters per second squared. I think you should get the correct answer even if you use 10, but it's up to you. One last thing you need to be very careful about is you cannot plug in PT equals 1 atmosphere. I know I said it's 1 atmosphere, but you need to plug this in SI units. That's because when you look at this combination of quantities here, you're kind of hoping that automatically this will all work out to be unit of meters. When you are relying on something like that happening simply automatically, then you need to use basic SI units, because 1 atmosphere won't cancel out with anything, but when it's in pascals, the basic units in pascals, kilograms, meters, seconds, they will all work out in a way that the final answer has the unit you are expecting. So all this comes down, for pressure at the top, you need to plug in 101.3 times 10 to the 3 pascals. So that's it. When you plug in numbers based on what I see here, you should get a number that's between 5 and 10 meters. If you get a number bigger than 10 meters, then something's definitely wrong. Because based on this number, I can quickly calculate in my head that the pressure at the bottom of the lake is close to 2 atmosphere, but not quite there. And about 10 meter of depth of water gives you about an atmosphere of pressure. So these are the two examples of applying ideal gas law. You will see more examples of using ideal gas law in the next chapter as we are working through heat engine processes. But now is the time for you to kind of thinking in terms of ideal gas law, so that if you are given, let's say, two quantities, pressure and volume, then it should be automatically for you that you figure out, oh, I am given enough information to calculate temperature, or I can express temperature in terms of those pressure and volume, and maybe an unknown number of gas particles that you will hope that will cancel out on each other later. So that's all. I will see you later. Bye. So question 12, it says, air is almost completely made up of nitrogen and oxygen molecules. And in case, for those of you who might not haven't taken chemistry yet, these are diatomic molecules. They have two nitrogen molecule has two nitrogen atoms bound together, and similar for oxygen. Yeah, both diatomic gases. And that will be an important fact. It says, answer the questions below. Now, let me go to the hint and show you what the hint points to, because there's a very specific thing that you should know. So when you click on hint, and it says, review section 2.3, capacity and equipartition of energy. And when you look at specific heat, that's when you have to start to consider some of the properties of ideal gas that go beyond saying that it's ideal gas. That there's a distinction between diatomic gas and monatomic gas. So when you go to the section, and you should read through that section more carefully. I'm just going to scroll through quickly looking for the thing that I'm looking for. Now, if you're simply using this, you'll get the wrong answer, because this is the result that only holds for monatomic ideal gas. So let me just, this is where it talks about now degrees of freedom. When people measure specific heat of real gases, they find that simply using this expression, it does not lead to correct result. What they find is that there's this number that you have to consider called the degree of freedom. With the monatomic gas, the degree of freedom is 3, and it actually matches up to 3 spatial dimensions, X and Y and Z, a translational degree of freedom. For a diatomic gas, there are two, well, there's technically 4 additional degrees of freedom, of which 2 are not frozen out. And if you might remember, if you took chemistry, either in high school or in college, you might remember this reference to degrees of freedom being frozen out. In fact, I think there's one of the conceptual questions that refer to that. And this plot is the thing that explains better than what I can ramble right now. If you want, you can take this as an experimental fact that if you have a diatomic gas, then at very cold temperatures, the rotational and vibrational degrees get frozen out. So you do have just the translational kinetic energy to contend with. Now, as this diatomic gas heats up, the rotational degree will start to be unfrozen, and that will come into play. And the whole freezing out business, it has to do with the quantum mechanics, which is why I don't want to get into it. But this is the kind of the room temperature range. So for the purpose of this class, for a diatomic, that is like molecules like nitrogen, N2, or oxygen, O2, and I guess CO2 gets more complicated, so we won't deal with that. But for diatomic gases, the degree of freedom is 5, and where that comes from is kind of rotation about. So, do I want to get into? Don't have enough props here. If you have, if you imagine kind of a molecule with the 2 atoms, then they can rotate about one axis that's kind of vertical here, or they can rotate about kind of this axis, And there's one other axis where they can rotate it, but if they rotate this way, then it doesn't look all that different. So there are two axes around which that diatomic molecules can rotate, and that's where additional 2 degrees of freedom come from. Now, with the diatomic molecules, there's actually 2 more degrees of freedom that has to do with the vibration, and those come from the vibrational kinetic energy and potential energy, and that's where this 7.5 comes from at very high temperatures. We won't really ever consider those temperatures, so we'll just stay down here for 5.5. So that's what you have to know for answering this question here, that you are dealing with diatomic gas, so you have to know that the degree of freedom that you are considering is 5. That's just something that comes from the fact that it's a diatomic gas. Now, I think a hint gets into this, or I guess I have this note here. So, you know, I don't, in this class, I'm trying to avoid using moles and Avogadro's number. So let me kind of show you how you can get from the equations that are in your textbook to the equation that you should be using for the way I write the questions in this class. So equation in your textbook is telling you that this is the specific heat capacity per mole. Molar heat capacity. So, so what that means is this is the heat capacity per mole of ideal gas when the process is under constant volume. So what your textbook is telling you is, so let me write down the textbook version. The specific heat capacity for a constant volume process per mole is degree of freedom over 2R. That, which means if you're trying to write out what is the flow of heat needed for certain amount of temperature change, then the expression would be this specific heat capacity times the number of moles of gas times change of temperature. Let me plug this in. Then you have the amount of heat needed for a particular temperature change is the degree of freedom over 2 times nR times the change of temperature delta T. And the version of the expression that doesn't rely on Avogadro's number, doesn't use moles, is one where you use this equivalence between the number of moles times gas constant and number of molecules times Boltzmann constant. You kind of see, you saw an aspect of this last week where I wrote down ideal gas law in 2 different forms. The form that I guess your textbook prefers is PV nRT, and that's also the version you saw in your chemistry class. But the version I will consistently use in this class is PV is equal to number of molecules, no moles, times Boltzmann constant times T. No Avogadro's number, no gas constant, and this is because I'm trying to minimize the number of arbitrary constants, and frankly, as it is, even Boltzmann constant is a bit of an arbitrary constant anyway. So, but I tolerate Boltzmann's constant. I won't tolerate gas constant. So with that in mind, really, what you can say is, instead of having so this is the molar heat capacity, you can actually have heat capacity per molecule. And the heat capacity per molecule would be simply D over 2 times the Boltzmann constant. This is the heat capacity per molecule. And if you look at the question, I give you the actual number of molecules, so you can just multiply with that actual number of molecules, not some number of moles that depend on what Avogadro's number is. So the expression to use for part A would be, okay, amount of heat that's needed. All right, so the heat that's needed is the specific capacity for diatomic gas. That should be 5.5 kb times the number of molecules, that would be this, times the change of temperature. So 10 degrees to 33 degrees C. So let me just write it out as, or change of temperature, 33 degrees C minus 10 degrees C. And I should have checked this first, that it's a constant value. I think I won't really get to constant pressure process until this week, because that deals with the first law of thermodynamics. So all the questions from problem set 2 should be constant volume processes. So that's the expression you should be using. And since there were more unusual number of people asking, let me just plug in the numbers to make sure I did this correctly. I just, well, technically what I want to be sure is I want to make sure that I didn't make any programming error in the question. 5/2 times number of molecules, 8 times 10 to the power 23 times 23 times, now let me plug in Boltzmann's constant, 1.38 times 10 to the power of minus 23, okay, equals 635 joules. Let me write that down here. Heat of 635 joule must be added. And let me just plug in to double check that it gets graded as correct and there's nothing I need to fix. 635. Good. So that's how you should do it. So hopefully people who are struggling with this just needed that thing about the degree of freedom. And I think that's, yeah, read carefully for the difference between specific heat of diatomic gas and monatomic gas. And the origin of that difference is that degree of freedom. Yeah. So for part B, it'll be basically the same calculation as what we did here, except that, you know, noble gases, they are all monatomic. They don't form molecules. So, you know, xenon, it's just going to be single atom particle. So the degree of freedom for the monatomic gas will be 3. So instead of 5/2, you'll have 3/2. And I can actually calculate the number here based on this. So I can divide it by 5, multiply it by 3. That should give me the right answer. So let me try that. Divide by 5, multiply by 3. So 381 joules. So yeah, these gases still can be considered ideal in some sense, as in nitrogen and oxygen are very different gases. But even so, for part A, if you have a gas of mostly nitrogen or even mostly oxygen, the answer here will be the same. That's the kind of amazing thing about ideal gas law, which is that a single law describes so many different types of gases. And with this kind of complication with degree of freedom, all you really have to know is what kind of geometric shape do the gas molecules have.